Good afternoon, everyone. It's truly a privilege to have with us this afternoon Professor Chihaya Adachi from Kyushu University. And as you know, I always point you back to the bio sketch on the brochure. Now there is, however, a couple of things that are missing and that I think are pretty important from the bio sketch that's in your brochure. That's the fact that after receiving his PhD and doing a number of things, Professor Adachi went for a postdoc to Princeton at the time when Steve Forrest was still there. And so he worked for 3 years at the end of the 90s with Steve Forrest, which means that while he will be talking about essentially the third generation of electroluminescent organic materials, he was also very much into the development of the second generation and the phosphorescent emitters. After his postdoc, he first got an appointment at that's the Shitose Institute of Technology, or of
yes,
where one of our excellent friends, Hiroyuki Sasabe, was president, and so started his academic career with Hiroyuki Sasabe, and then became professor at Kyushu University in Fukuoka, or in the suburbs of Fukuoka, where he's still now, and he is certainly an extremely sought-after speaker, especially because of the impact that his research has had in organic electronics and photonics. And so we are extremely grateful that you found a little bit of time in your extremely busy schedule to come and visit us today. And Chihaya is on his way actually to SPIE, to San Diego, for the next week meeting over there. So without further ado, again, thank you very much for being with us today. And Chihaya, the floor is yours.
Okay, thank you very much, Jean-Luc, for your kind introduction. I'm Chihaya Adachi from Kyushu University, Japan. And actually, I have a jet lag and very sleepy. And so we have a 12 hours time difference. So in Japan, it's midnight. And I try to do my best. And okay, so today I'm very happy to deliver you our new technology, third generation electroluminescent material. This is basically delayed fluorescence, which also realized 100% internal electroluminescence efficiency. So as you know, the first generation, this is the fluorescence, and the second generation, the phosphorescence. And the phosphorus technology also realized 100% internal efficiency. So everybody supposed the phosphorescence is the solo solution to get the high efficiency. But today, I want to show you that we have another way to get high efficiency. This is the delayed fluorescence. So in the event of Hall and electron recombination, so we have a 25% singlet excisions and 75% triplet excisions due to spin statistics. So as far as we use the singlet excisions, the internal efficiency is limited to 25%. Even we fluorescence efficiency is 100%. On the other hand, phosphorus, so due to 75% exciton formation, and also we can expect the intersystem crossing from singlet to triplet. So when we use the iridium complexes, which allow the radiative decay from a triplet states, we can get the 100% electroluminescence using the iridium complexes. So actually 2000, using iridium PPY, which show the 100% intersystem crossing and 100% phosphorescence, almost 100% electroluminescence was realized using these molecules. So, okay, here I show you the advantage and disadvantage of fluorescence and phosphorescence molecules. So, typical fluorescence molecule is the LQ3 aluminum quinoline, and this has rather short transient lifetime of the 15 nanoseconds, quite short lifetime. And although the exciton production efficiency is the rather low, 25%, we see a rather weak exciton annihilation under high current density, and molecular design is unlimited, and the cost is rather cheap. So on the other hand, phosphorus. So we have a typical three choices. One is the IRPPY. In this case, the emission comes from metal ligand charge transfer states, and PTOEP. In this case, the emission comes from the ligand pi-pi star triplet states, and European complexes. In this case, with the optical excitation, the ligand absorbs the light, and we have a formation of singlet states and intersystem cross to the triplet states, and the energy is transferred to the europium, and the emission comes from the FF transitions. So anyhow, using phosphorescence technologies, in theoretically we can get the very high efficiency up to 100%. However, we see a rather strong exciton annihilation because of the rather long excited lifetime, microsecond to millisecond. And also the molecular design is limited. We have to use the metal complexes, and also the cost is rather high. There is a discussion, and actually the iridium chloride, it costs $200 per gram, so it's not a cheap molecules. So fluorescence and phosphorescence, this has an advantage and also the disadvantages. So today, I want to show you the new way to harvest electrically generated excitons. This is our idea. So our idea is alignment of singlet and triplet excited states. So once we align the two states, triplet exciton upconvert to singlet and gets the emission as the delayed fluorescence. So this is our idea. So basically, first order mixing coefficient between singlet and triplet states, lambda is proportional to a spin orbit coupling. So most of the aromatic compound contain no heavy metal atoms. The spin orbit coupling is weak, but if we prepare the small energy gap between singlet and triplet, so the lambda is inversely proportional to the delta ST, we can upconvert triplet exciton into singlet even with the simple aromatic compounds. So we try to design the molecules which has the small delta ST and upconvert triplet exciton into singlet and gets the emission as the delayed fluorescence. This is our strategy. So we try to find the molecules which show the thermally activated delayed fluorescence, and we started from a porphyrin compound which is known to show the delayed fluorescence in analytical chemistry. Okay, we synthesized these molecules, and during the synthesis of this molecule, we found very unique photoluminescence characteristics. So okay, we put the material into a TLC plate, and we heat it up and shine the UV light, and we show the very unique photoluminescence characteristics. So this is the emission intensity depending on temperature. So this is the freezing point, this is the 30 degrees centigrade, and this is the boiling point. So with the increase of the temperature, we see the increase of the photoluminescence efficiency. As you know, most of the molecules show the decrease of the PL quantum efficiency with the increase of the temperature because of the increase of the non-radiative decay process. But this molecule showed very opposite behavior. So we carefully analyzed the transient decay using a streak camera. This shows the transient decay at the room temperature, and this is the elevated temperature of the 400 K. This is the low temperature of the 5 K. So transient behavior was quite different. So at room temperature, you could see 3 different emissions. This is the prompt fluorescence, and after that, you could see the delayed component. This is the delayed fluorescence, TADF, and this is the phosphorescence. So at room temperature, we could see 3 emission paths: prompt fluorescence, TADF, and phosphorescence. On the other hand, at the elevated temperature of the 400 K, so the phosphorescence was completely disappeared. Instead, we see the strong appearance of the TADF. On the other hand, at 5K, we could see the strong appearance of the phosphorescence. On the other hand, delayed fluorescence was completely disappeared. So this is because the energy gap between singlet and triplet is the 0.24 electron volt. So as the low temperature, triplet exciton cannot overcome this energy barrier and resulted in an appearance of the phosphorescence. On the other hand, at elevated temperature of the 400 K, triplet exciton efficiently upconvert and resulted in TADF. So very unique photoluminescence behavior we observed with the porphyrin compound. So here I show you the absolute PL quantum efficiency of 3 components. So red line show the fluorescence efficiency, and the green line show the phosphorescence efficiency. So it's show the almost constant and gradually decreased at the temperature higher than 300 K. And instead, we see the appearance of the delayed component over the temperature higher than 300 K. So, but I should say, even at the 400 K, the absolute PL quantum efficiency of TADF is just 2.5%. So it's very low number. So anyhow, we prepared the OLED structure, ITO, P.PSS, SNF2 OEP dispersed in polyvinyl carbazole, and we put the mag silver as the cathode. And we apply the pulse voltage to the device, and we see the transient EL. So we could clearly see the prompt emission and delayed emissions. So this is the first observation of the delayed fluorescence and the electrical excitation. So, but I should say, EL quantum efficiency at room temperature was the 0.1%, and even elevated temperature of 400 K, the EL efficiency was the 0.3%. So, although we observe the delayed electroluminescence efficiency is quite low, so although we published in Applied Advanced Material 2009, nobody interested in the result because of the low efficiency. So then we try to design the new molecules which show the efficient delayed fluorescence. So here I show you our new molecules, which was disclosed in the APL and the physical review letter and APL. And today I want to show you this molecule and this molecule. Okay, so how can we design the molecules which has a small delta St? So the design rule is rather simple. So as you know, delta St is basically proportional to the exchange energy, and exchange energy is given by this formula, and this formula tells us basically K is proportional to the overlap integral between HOMO and LUMOS. So if we have a large overlap between HOMO and LUMO, so if the orbital has a similar orbital, we get the rather large delta St. On the other hand, if HOMO and LUMO has the orthogonal relationship, we get the small delta St. So design rule is rather simple. So to realize this relationship, we introduce the molecules which contain both electron donating and electron accepting unit into one molecule, because the HOMO localize at the electron donating unit and the LUMO localize electron accepting unit. So we expect the separation of HOMO and LUMO, and to enhance the localization, we introduce the steric hindrance between donor and acceptor units. And basically, but here we need a very delicate design. Basically, radiative decay rate, oscillator strength is proportional to the overlap integral. So if we have no overlap between HOMO and LUMO, molecule never show luminescence. So we want to separate HOMO and LUMO, but we need a small overlap to maintain radiative decay rate. So then we actually synthesized 100 organic molecules, and we encounter the promising molecules PLC-TRZ, which is composed of the triazine, biphenyl triazine electron accepting unit and indrocarbazole unit. This is the electron donating unit. So molecule is composed of 1 electron accepting and 2 electron donating unit. And this phenyl ring induced the steric hindrance, so the indrocarbazole is rather standing against the triazine unit. So as we expected, HOMO localized at the indrocarbazole unit and the LUMO localized at the triazine unit. So we could separate HOMO and LUMO, and actually we have a small overlap around here. And we really surprised that we get a very small difference between fluorescence and phosphorescence. So, okay, black line show the fluorescence and the red line show the phosphorescence, and from peak to peak, we can estimate that delta St is just 100 millielectron volt. It's a very small energy gap between singlet and triplet. So here I show you the basic photoluminescence behavior of PLC-TRZ in a toluene solution, and this is the transient decay, and you can see both prompt and delayed components, and this was obtained with the argon bubbling. This means oxygen was completely removed from the solution. On the other hand, if the solution contains oxygen, so no argon bubbling, the delayed component was completely disappeared. This is because of the triplet exciton quenching by the oxygen. So clearly indicating the delayed component is due to the upconversion from triplet to the singlet delayed fluorescence. So to understand the photophysical characteristics, we measure the temperature dependence of the PLC-TRZ dispersed in MCP host matrices. So black line show the fluorescence efficiency showing almost independent of the temperature. On the other hand, TADF, we could see the appearance of TADF over the temperature of 100K, and it gradually increased, and over the 200K, it gradually goes down. On the other hand, at the low temperature, we could see the appearance of the phosphorescence. This is the very characteristics emission, so we can well distinguish the phosphorescence and the delayed TADF. So totally, we could obtain a maximum photoluminescence efficiency around 45%. So very efficient compared to the Prophylene compound. So last year, we designed advanced TADF molecules composed of the triazine and biphenyl carbazole. We call this molecule CC2TA. And from the DFT calculation, we obtain delta ST is 0.06 electron volt. So 60 milli electron volt we obtained. So the same manner, we obtain a separation of the HOMO and LUMO, and actually we observed a large distortion between electron donating and electron accepting unit that's enhanced the separation of HOMO and LUMO orbitals. Okay, so this is the transient decay. We could see both prompt and delayed component, and the prompt lifetime is the few nanosecond, and the delayed one is the microsecond orders, as you can see. So this is the temperature dependence, and this is the low temperature. With the increase of the temperature, delayed component was increased. So you could see yellow line is the prompt component, and the prompt one is almost independent of the temperature, while the delayed component, it gradually increased with the increase of the temperature. So around the room temperature, the PL quantum efficiency exceeded to the 60%. So we want to use this molecule for the OLED. So we are interested in photoluminescence characteristics in solid films, and we dispersed CC2TA various host molecules here. So the BSB, UGH2, and DPPO, PYD2, and MCP we used as the host. So this figure shows the PL quantum efficiency against the triplet energy of host layers. So when we use the host having a triplet energy higher than 3.1, we obtain a high TADF efficiency. On the other hand, when the triplet energy of host is lower than 3.1, TADF efficiency goes down dramatically. This is because of the imperfect confinement of the triplet exciton by host layers. So similar to the phosphorescence device, we have to employ the host molecules, DPPO and UGH2, having a wider energy gap. So using UGH2 and a DPPO, we can get the large amount of the delayed component, and the total emission efficiency exceeded to the 60%. So we prepared the OLED device, and actually we prepared lots of OLED device structures, and most of the device show the EQE, external quantum efficiency, higher than 12%, and with the optimized device structure of the device 3, we could reduce the driving voltage down to 9 to 2 electron volt. So that basically we want to confine charge excitons and also the charge carrier into the emitting layer, and device 3 satisfy the, such kind of condition. So we can get the high yield efficiency and also the low driving voltage. So here, let's compare the EL and the PL process. So PL process, actually we irradiate the light and the molecule absorbs the light. So we have a formation of the 100% singlet exciton formation, and promptly decay 15.6% and 84.4% decay to the triplete states, and this exciton up convert and down convert. This process continues until exciton gets the thermal equilibrium. So totally we can say 84% down convert and 46.5 up convert, and resulted in a delayed fluorescence. So delayed fluorescence efficiency is 46.5%. So on the other hand, in the electroluminescence, we have a 25% singlet exciton formation and 75% triplet exciton formation, and these excitons up convert and down convert, and also these exciton down convert and down convert triplet and up convert. So totally we can say prompt efficiency is 2.5 and the delayed component is 53.7%. So PLQI is we can expect that 62.1%, and the theoretical EQE we can expect 11.3%. So this is the good coincidence, good number. Good coincidence with the experimental obtained EQE. So we further try to enhance the delayed component, and we continue to synthesize the molecules, and we encounter the very efficient TADF molecules. So this is our molecules. It's a very simple molecules, and again, the molecule is composed of the electron accepting dicyanobenzene and also the carbazoles. So, and actually, this molecule shows the PLQI close to the 100%. So, with the device structure of the OLED device structure of NPD and 4CZ IPN was dispersed in a CBP and TPBI and lithium fluoride with a very simple structure. We obtain a maximum EQE of the 20%. So by assuming the light-out coupling efficiency of 20%, we can say the internal EQE is close to 100%. So this molecule can convert 100% electron into photons. So we can also tune the emission colors from blue to orange emission, but just changing the substituent. So from the reverse intersystem crossing rate, we can temperature dependence of the reverse intersystem crossing rate. We estimate the delta ST experimentally, so 83 milli-electron volts. So this is not a very ultimate small, but quite small number compared to the conventional fluorescence molecules. So okay, so here I want to show you the energy diagram of these molecules. So this is a kind of CT complex, and the molecule has 3 excited states. One is a singlet CT state, the other is a triplet CT state, and the molecule also have a localized triplet states. So in case of the 4CZ IPM, localized triplet state is very close to the CT triplet states. So then up conversion is very efficient, so we can get a rather short transient lifetime. In case of 4CZ TPM, localized triplet state is higher than localized CT and CT singlet and triplet, so that we can get the rather short lifetime. And in case of the 2CZPN and 4CZPN, so we get the rather long transient lifetime. Okay, so everybody interested in reliability of the device performance, and we prepare the OLED device structure, and we test the reliability test. So this is our device structure, which is composed of ITO, HATCN, and the TRZ, and emitting layer, T2T, and BPY TP2. These 2 layers is the electron injection and transport layers. So with these device structures, we change the concentration of the dopant concentration, and from 3 weight% to 15 weight%, and we also prepare the reference device of the IRPPY 6 weight%. So you could see with the optimized concentration around 6 to 3 weight%, we obtain a very efficient luminescence efficiency reached to the 50 candela per ampere. And how about the reliabilities? So we get very promising results. So okay, this line is the reference device IRPPY, and okay, we change the concentration 3%, 6%, 10%, and 15%. So with the increase of the dopant concentration, we could see improvement of the reliability. So with in case of 10% and 15%, actually we could see the better performance compared to the IRPPY. So so from this result, we can estimate the projected half-life time LT50 is 3,000 hours. So we didn't use the best surrounding molecules. So we are a university and we don't have best molecules, but even though with conventional molecules, the lifetime is quite promising. So we expect that this molecule can be commercialized in the near future. So, so here I shortly mentioned the degradation mechanisms. So here we prepare the hole-only device and the electron-only device, and with the variation of the dopant concentrations. In case of the hole-only device, so we see the almost same IV characteristics. On the other hand, in case of the electron-only device, so electron is injected here into the emitting layer. In this case, we see the very large variation of the IV depending on dopant concentration. So higher the dopant concentration, we see the better the IV characteristics. So this means basically electron transport is limited to this dopant levels. So in case of the low concentration of the dopant, electron cannot into a emitting layer. So we have a charge accumulation of electron between T2T and MCBP. In case of the higher concentration, electrons injected from T2T to the dopant level and electron transport happened. So from this result, we can say the degradation is basically related to the charge accumulation between electron transport and emitting layers. So the efficient injection of electron relax the degradation. Okay, we also try to enhance the blue emissions, and last year we reported the very promising blue TADF using a simple molecule of the cyano derivatives. Okay, so again the molecule is composed of the electron accepting and 2 electron donating unit, and this molecule showed a very pure blue peaked at the 440 nanometer, and the CIE sits around the 0.15 and 0.07. So very pure blue we obtained. And this is the EQE, and okay, here I compare the typical phosphorescence molecules, and at the maximum EQE was comparable to the IR-FPPZ, and unfortunately it showed a rather gradual decrease of the EL efficiency, but we can relax this behavior by optimizing the device structures. Anyhow, we can get the EQE of the 10%. Okay, let's see photophysics of the these molecules. So here I compare the 3 donor substituent, and okay, this shows very unique photoluminescence characteristics. So okay, blue line is the prompt emission fluorescence emissions, and red line is the phosphorescence emissions at the 77K. So in case of the okay, so okay, so here okay, phosphorescence was very we could see the vibrational behavior, and this shape is quite similar to the triphenylamine and carbazoles. So here I compare the okay triphenylamine phosphorescence, and this is quite similar shapes. And okay, this is the carbazole emission spectrum, and this is again very similar to the carbazole emissions. So this indicates the localized triplet states is due to okay, the bottom localized bottom of the triplet state is localized emission based on carbazole and triphenylamines. So I want to say the use of the carbazole is effective to induce the blue shift compared to the diphenylamine unit. So okay, this is the transient decay of the 3 component, and you could see when we use the number 3, we could see the very strong appearance of the delayed luminescence. So we also calculate the optimized structures, HOMO and LUMO, and we observe the introduction of the carbazole induced rather large steric hindrance between donor and acceptors. So again, from the calculation, we can say the introduction of carbazole unit is better than diphenylamines. Also, most recently, we reported the possibility of the LED emitters using a MEREM unit. Again, this MEREM unit is a strong electron accepting unit and triphenylamines electron donating unit, and we can say HOMO localized in a triphenylamine unit and LUMO localized at the MEREM unit. So, this molecule showed a rather different behavior compared to the another TADF molecules. So this is the photoluminescence decay, and in case of the photoluminescence, we could see the very weak, very faint delayed component. We are almost missed the presence of the delayed component, but we could surely see the presence of the delayed component, but the component is quite weak. So, but on the other hand, under the electrical excitation, we could see the very strong appearance of the delayed component, although the photoluminescence delayed component was quite weak. This means this molecule is very efficient, close to the 100%, and under the optical excitation, most of the singlet exciton radiatively decay, and intersystem crossing is quite weak. But under electrical excitation, automatically 75% triplet exciton that convert to singlet and appearance of the delayed component. So we have to be careful, even though we see a very weak delayed fluorescence, some molecule show the TADF characteristics. So under electrical excitation, we could see the delayed EL. So anyway, we obtain a maximum EQE close to the 18%, and lambda max was the 610 nanometer. So we need more redshift to get the pure red emissions. So last 2 years, we reported the series of the TADF molecules, and this is the blue emitters, and we reported the spiral derivatives. This is also the promising results, and various kind of the triazine and carbazole, indole-carbazole units show the strong appearance of the TADF, and also the cyanobenzene derivatives and MEREM unit is also really promising. Still, we are trying to expand the TADF technologies. Okay, I shortly talk about another way, the Exciplex formation. So actually the TADF is a kind of intramolecular charge transfer, but also Exciplex is also promising. Exciplex is always observed in OLED at the interface of the hot transport and electron transport layers and MTD-ATA. In case of the MTD-ATA and PBD, we observe the emission from the Exciplex. So the electron transition from a LUMO or PBD into a HOMO on the MTD-ATA. That means Exciplex is the basically separation HOMO and LUMO is realized in an Exciplex. So we carefully analyze the transient decay of the Exciplex, and the Exciplex actually show the both prompt and delayed emissions. So delayed emissions slightly redshifted, but almost similar emission spectrum we obtain in Exciplex emissions. Okay, from the spectroscopic data, we can depict the energy level and like this, and the Exciplex singlet and triplet is lower than MTD-ATA and PBD, and Exciplex triplet is just below the singlet states, so that we can expect an efficient up conversion and resulted in delayed fluorescence. Okay, this shows that transient decay of the EL and PL. So due to the 75% of the triplet excitation formation and electrical excitation, we could see the stronger appearance of the delayed component compared to the photo excitation. And from this result, we can estimate reverse intersystem crossing is the 87%, so almost 90% up conversion. So very efficient. And also from the rate of the reverse intersystem crossing, temperature dependence, so we can estimate the from the Arrhenius plot, we obtain a 50 millielectron volt. So small energy gap and an efficient reverse intersystem crossing in an Exciplex system. So one of the drawbacks of the Exciplex is rather low quantum efficiency, and selection of donor and acceptor may enhance the Exciplex emission, and we found the combination of MTD-ATA and PPT showed a rather good performance. In case of the MTD-ATA and PPT, the PLQI of Exciplex is the 28.5%, but the delayed component is 25.4%, so we can expect efficient exciton formation through triplet states. And actually, with the even in the Exciplex formation, we obtain a EQE of the 10%. So everybody suppose Exciplex is useless in OLED, but okay, this is the I want to say Exciplex is also promising for the high efficiency OLED. We are now trying to enhance the Exciplex emission, and actually we get the better number than this result by optimizing materials. Okay, so I'd like to talk about the positioning of the three emitters. So the fluorescence, cost is low, but the efficiency is low. The phosphorescence, so the efficiency is high, but the cost is rather expensive. So the third generation, we named the hyperfluorescence. Delayed fluorescence technology satisfy both high efficiency and low cost. So there is no reason without using TADF molecules. Okay, and before I close my talk, I want to shortly talk about the our city of the Fukuoka. This is map of the Japan, and Fukuoka is located to the south part of the Japan, Kyushu Island, and this is map of Fukuoka, and airport is here, and university is here, and we are faced to Japan Sea, and in a summertime, and we have a very beautiful four seasons. In the summertime, you can enjoy the fishing. So the fish comes in and trapped. So the university is here, just 10 minutes driving. You can get lots of fishes, and when students run out of money, they go there and catch the food. Okay, and this is our campus, so Kyushu University. Okay, so yeah, if you have a chance to come to Japan, so please stop by Fukuoka. Okay, and finally, I'd like to thanks my collaborators, the Opera research teams, and this was the governmental project, and we have a special research team, and we have 15 company researchers and working together in the universities, and every week we have 10 new TADF molecules, and we really enjoy the TADF technologies. Okay, thank you very much for attention.
Thank you so much, Chihaya, for sharing those beautiful work with us this afternoon. Are there questions or comments? Seth?
Questions that may be related. One is, what happens when you go higher than 15% in your loading of the dopant in the host?
Oh, you mean a reliability test?
Well, or just in terms of efficiency.
Unfortunately, efficiency goes down due to the presence of the concentration quenching.
Okay.
So the as far as the PL quantum efficiency, 6 to 10% is best. But in case of reliability, 15 to 20% is better. But we understand the problem is the electron accumulation at the interface of the electron transport and the emitting layer. So because of the CBP does not transport electrons efficiently, so we replace the host molecule to the electron transporting molecules, so we get the better reliability. So the bipolar host seems more promising.
That's the second question.
Okay. In terms of the variations that you had in the benzenes substituted by the carbazoles and the cyano groups, so do you have a rationale for the way the local excited state moves with respect to the charge transfer states?
Actually, the triplet state, localized triplet state seems unchanged against the substituent, but CT singlet state and triplet states move by changing the substituent.
And so the local triplet state is on the benzene, or is it on the carbazole?
Carbazole. Yes, carbazole.
That's just the carbazole.
Yes, always. In case of another TADF molecules, always the localized triplet state sits on the carbazole.
You want?
So I have a question. Is with the increase of temperature, it seems that the TADF get prominent, but at the same time, it seems like the phosphorescence contribution gets also quite small and even disappear. So statistically, we always have some portion of the triplet, and so we have a portion of the phosphorescence contribution. So can you explain why this is the case?
Okay, I couldn't very understand what you're talking. And so
from some of the results, I find the contribution of the phosphorescence get even much smaller and disappear
at a higher temperature, yes, because of the up conversion.
Yeah, but statistically, we always have some portion of that contribution, I think. But why it disappears?
Why disappear? Okay, so the 3-bit exciton up convert to singlet and contributed as delayed.
The gap of singlet triplet is not zero. So I think at final temperature, we always have some portion of the triplet.
Yeah, but if the K from the singlet is fast, if the K from the triplet is fast, it just drains.
Yeah, but
it's slow.
I'm sorry,
Yeah.
slow from the triplet, then
Yeah.
it just drains out through the singlet channel.
So if you have, you know, the equilibrium, I mean, between the inter-system crossing and the reverse inter-system crossing, if they go both ways almost equally fast, I mean, then if the singlet goes down extremely quickly, as Seth says, it will drain the whole thing.
Mm-hmm. Yeah.
So,
Yes.
I don't see any hand asking for another question or comment. So let me again thank Professor Adachi.
Thank you very much.
And remember that everyone is more than welcome to attend the reception that, as usual, will be on the second floor atrium. So please don't leave the building, Tim, but go to the second floor. And also, there is a little thing that I'd like to hand to Professor Adachi, which is...
Okay, yeah. Thank you very much.
And so the